All right, in this section we're going to find derivatives of products and quotients. So we begin with a theorem on what we call the product rule. So if f and g are both differentiable functions, then their product is differentiable. And it is given by this formula, right? So the derivative of f times g is equal to g times f prime plus f times g prime. Note, I think what's of particular importance to note is that the derivative of a product, f times g, is not equal to the derivative of f times the derivative of g. Like, we can't split up a derivative over a product the way we can with addition. So we're going to get some practice using the product rule. And the first step in using the product rule is recognizing when you've got a product, when you need to use the product rule. We need to use the product rule if we're multiplying two things together and they both have a variable, right? They both have the x. So here our function is h of x. It's x squared plus 3 times 3 minus 2x. This is a product. Now, before we start this, you might note that, well, we could do some algebra, right? We could FOIL out that product and then we have a polynomial. And that is true. You absolutely can do that. But there's going to be so many functions where we have no choice but to use the product rule. So we're going to make sure that we get practice using the product rule, and then we know we're already pretty good at it when there's no way to avoid it. So when we have a product, right, when we identify the product, then we've got to just identify our f and our g. So our f function here will be the first one. And with the product rule, it really doesn't matter, right, which one's f and which one's g, because multiplication is commutative, but I kind of default to letting the first function be f. So f is x squared plus 3. And if f is equal to f squared plus 3, then its derivative, f prime, now we're just using our rules from the last section, this is 2x. Our g function is 3 minus 2x, and again, using the rules from the last section, g prime is negative 2. So now I've done the work kind of setting this up. I have everything I need. So h prime of x, the derivative of our function, I'm just writing out the product rule, g times f prime plus f times g prime. I write out the product rule every time I need to use it, because then when I need to know it, chances are I'll have it memorized, even if I wasn't trying, right? So g times f prime, that's a 3 minus 2x, times f prime, that's 2x, plus f is x squared plus 3, times g prime, which is negative 2. Now, what we have written, this is equal to h prime of x, but it's just, horribly unsimplified, right? We need to communicate our answer effectively. Let's simplify this. I'm going to expand each of these products. So we got 6x minus 4x squared, and then distributing that negative 2, minus 2x squared, minus 6. And combining some like terms, we get a negative 6x squared plus 6x minus 6. There's our h prime of x. You could write it like that, or if you want, it's pretty clear we could take out a factor of 6. I'll take out a factor of negative 6. Either is fine. X squared minus x plus 1. Alright, so there's our derivative. Let's try another one. We're going to find dy dx for this function. Again, we've got a product, and we see that there's x's in both factors. So our f function is the first guy here, 3 minus x minus 2x squared. And if that's f, then f prime, its derivative, using the rules from the last section, that's a negative 1 minus 4x. Our g function is x to the 4th minus 4, and in that case g prime, its derivative is 4x cubed. Alright, so dy dx we're going to find using the product rule. That's g times f prime plus f times g prime. And now I'm just going to plug in the expressions over here on the right. So g times f prime, that's x to the fourth minus 4 times -1 minus 4x plus f times g prime, that's 3 minus x minus 2x squared times 4x cubed. Again, what we have written here is equal to dy dx. It's just really awfully unsimplified. It's not pleasant to look at. It's hard to use. So we're going to simplify this, and we're going to do that by expanding all the products. So I'm going to, I guess we'll FOIL out this first product, or you could set up the grid. I'm just going to kind of distribute. Let's see, if I distribute the x to the fourth, we get a negative x to the fourth minus 4x to the fifth. And then distributing the minus 4, we get a plus 4 plus 16x. Now I'll distribute the 4x cubed in the other product. That's plus 12x cubed minus 4x to the fourth minus 8x to the fifth. Alright, now we have some like terms to combine. So let's see, our highest power, we've got our x to the fifths here. That's a minus 12x to the fifth. And then we have x to the fourth. That's minus 5x to the fourth. And then we have a plus 12x cubed plus 16x plus 4. And there's our dy dx. Again, you could have found dy dx by first, maybe multiplying out first, right, that product, and then just, using our shortcuts on the polynomial that results. But we really want to make sure we're getting practice on using the product rule now, and it's particularly helpful to get practice on that when we even have another way, so we could kind of check our work. Because there's going to be lots and lots of times when we can't avoid having to use the product rule. Alright, so we have a similar rule for finding the derivatives of quotients, right, if we're dividing two functions. And it looks really similar to the product rule. The difference is that we are subtracting up here. Right, so first of all, it absolutely matters which one is f and which one is g. F has to be the function on top, and g has to be the function on the bottom. And then you're subtracting, right? So you find the same kind of products, right? G times f prime and f times g prime, but you have to subtract them. Also, because we're subtracting, it matters which one comes first. So you've got to have the gf prime first. And then, of course, it's all over g squared, and that's another change, another way in which it's different from the product rule. Alright, so we are going to find q prime of x, where q of x is this rational function. It's a fraction, and much like with the product rule, the first step in using the quotient rule is recognizing when you need to use the quotient rule. So we've got a fraction, and I have x's both on top and the bottom, right? So there's my dead giveaway. I really need to set this up with the quotient rule. My f function is on top. That's 3 minus 2x. And then f prime, using our shortcuts, is -2. Our g function is on the bottom. That's x squared plus 2. And let's see, using our power rule, g prime is 2x. So now q prime of x, setting up the quotient rule, g times f prime minus f times g prime all over g squared. So now I'm going to just plug in the expressions I need from the work I did over on the right. G times f prime, that's x squared plus 2 times -2, and then I'm subtracting f times g prime, that's 3 minus 2x times 2x. On the bottom, we have g squared. It's not g prime squared, it's g squared. It's the original denominator. So that's x squared plus 2 squared. Now from here, what we want to do is expand the products in the numerator in order to help us simplify. But like we've seen in the past, that denominator is factored, is in a nice factored form. The numerator is not factored, right? Because we see products, but then we're subtracting them. So the numerator is not in a factored form at all. So that's why we need to expand those products. But the denominator is factored. It's just the square of x squared plus 2. So we're going to leave the denominator in factored form. So let's see, doing some distributing, we have a minus 2x squared minus 4 up top. Now I've got to be careful here. I'm going to distribute this 2x and the negative at the same time. Okay, so watch me here. Make sure that I do it right. So I've got a 6x, a negative 6x. I've got a negative 4x squared, so that'd be a plus 4x squared. And this is all over the square of x squared plus 2. We can combine some like terms. Up top, that simplifies to a positive 2x squared minus 6x minus 4 over the square of x squared plus 2. And you could leave it like this, or, up top we can take out a 2. I'm just going to yank out a factor of 2 from the numerator. X squared minus 3x minus 2. And there is our q prime of x. All right, let's try an applied problem. In this next example, they tell us that the concentration, which is given in milligrams per milliliter, of a certain drug in the bloodstream is given by this function here. So we've got C equals 25t over t squared plus 5. So note that it's a fraction, and we have variables in both the top and the bottom. So this is where t is the time in hours. So if we knew, how many hours have elapsed, we could use that function to tell us what the concentration of the drug is in the bloodstream. They ask us to find dc dt. Okay, so we're going to take the derivative, but we'll just note that's a time rate of change, right? That's the rate of the concentration, the rate of change of concentration with respect to time. So it tells us that as time is elapsing, how fast that concentration is changing, and in what direction. Because if we just sort of think, we're gonna find the derivative, and then maybe take a look at the graph of the derivative. But if we just try to think about what we would expect to see happening, the concentration itself, right? So imagine right before you take the drug, right? There's none of it in your bloodstream. So concentration 0. Then you take the drug, so that concentration is going to increase until it reaches some peak. And as you take it, after you take it, your body is working to filter it out. So your body is filtering it out, and then that concentration will then decrease over time. So we kind of maybe can picture what we might expect the concentration graph to look like. And then we're going to compare that to what we found for the derivative. So our function, c equals 25t over t squared plus 5. So our f function, always on top, that's 25t. And f prime is 25. Our g function is the bottom one, that's t squared plus 5. So then g prime is 2t. dc dt, well, we're going to use the quotient rule, so that is g times f prime minus f times g prime all over g squared. G times f prime, that's t squared plus 5 times 25 minus f times g prime, that's 25t times 2t. This is all over g squared, so the square of t squared plus 5. Alright, so this is equal to the derivative, but of course not simplified, and we want to simplify it. And just as we saw in the last example, What we're going to do here is expand each product in the numerator. And we're going to leave the denominator factored. So up top, distributing that 25t squared plus 125, and then minus 50t squared. We can combine some like terms. So we've got a minus 25t squared plus 125. And then we can take out a 25. In fact, I guess I'll take out a negative 25. And then inside we've got t squared minus 5 when we factor that out. And when you look at this, I don't know about you, but I look at this and I think, oh man, I wanted it's so close to be able to cancel something, but we just can't, right? So t squared minus 5 and t squared plus 5 are just totally different factors. And there is no reducing we can do. So here is our derivative. This is the instantaneous rate of change of the concentration with respect to time. So we've done what they've asked us to do, but now let's do some analysis. Let's look at this function. I'm going to put two functions in the calculator and look at their graph. So first, I'm going to put in the original function, 25t divided by t squared plus 5. So my y equals editor, let me clear these out. 25x, our calculator just wants to use x, so we're going to graph y as a function of x, understanding that that means that we have c as a function of t. So 25x divided by, I need parentheses around the bottom here, x squared plus 5. Now, if I think about logistical restrictions on the domain, t is not going to be negative, right? We don't need to see what's happening when t is negative, because this function is really only becomes valid at the instant the drug is taken, and that's t equals 0. So my t only needs to start at 0, and so that's x starting at 0, and maybe I'll go up to like, I don't know, 10. I might have to make some adjustments here. The y min is the concentration. Now the concentration will never be negative, but I'm going to view the derivative function on the same set of axes eventually. So I'm going to let this go down to say like minus 5, and maybe I'll let the y max go up to 5. I'm just going to see how this looks, see if I need to make any adjustments here. Let's look at the graph. Alright, looks like I need to go up a bit on the y-axis and out a bit on the x-axis. So I'll go up to 10 on the y, and maybe I'll go out to 20 on the x. Okay, so that's sort of what we expect to see, right? That's what we talked about in the beginning. At the instant the drug is taken, you've got no drug in your system, but then you take the drug and that increases, right? So this is a graph, this blue graph, of the actual concentration. This is not the derivative. So we see the concentration increasing, it reaches some peak here, and then it starts decreasing because your body is working to filter it out. Now I'm going to add to this the graph of the derivative. So that was minus 25 times x squared minus 5. And this is all over parentheses x squared plus 5 squared. Let's see how this looks. Alright, so there's the red graph is our derivative. It starts positive, right? The derivative itself is positive because the rate of change, like the concentration, is increasing, right? If the concentration is increasing, if the blue curve is increasing, that corresponds to the red curve just being above the x-axis. All right. Now look at what happens right here. at the spot where the red curve is 0, right, crosses the x-axis, that corresponds perfectly to where the blue curve reaches its peak, right? The derivative is 0 there. You could visualize it, right? If you draw in the tangent lines right at the top here, that's a horizontal tangent line. A horizontal line has a slope 0, and so that's why the red curve crosses the x-axis. It's 0 there. And then for the rest of it, the red curve is negative, right? It exists below the x-axis, and that's because the derivative is negative. The concentration is decreasing. So the part of the curve that is decreasing corresponds to where the red curve is below the x-axis, where the red curve is negative.